Hi guys, this is Avionics, equipment of civil airplane, and this is Ivan, and we will continue talking about digital data buses of modern airplane. And today we will just introduce two quite useful buses, which is MIL-STD-1553B and ARINC 629. It is important that MIL-STD-1553B is a military data transferring standard. However, it plays an important role because it was one of the useful network topology, which support like real package transferring and satisfy requirements of federated avionics, because it support multiplexing and using subnetworks inside of particular line replaceable unit. Therefore, it is important to talk about it. And ARINC 629, it is a further development of ARINC 429. However, it has absolutely different performance and different principle of data transmission. Thus, we need to talk about it. And first of all, we start to talk from describing MIL-STD-1553B. First of all, I would like to specify that MIL-STD, it is a military standard of USA. Thus, two subwords, MIL and STD. Here STD means standard and MIL means military. And then we've got a number of specification. In military aviation, it was first specification for digital data transmission on board of airplane. First published in April 1973. Firstly used on board of F-15. Support much more speedy bit rate, up to 1 megabits per second. If you remember, ARINC 429 can support up to 100 kilobits per second. Thus, MIL-STD much more speedy for data transferring. However, MIL-STD have to use a specific equipment which called bus controller to organize network operation. It supports up to 30 line replaceable units in one network and use the same physical level as ARINC 429. It means two wires twisty paired. Okay. First of all, let me introduce a bus controller. In order to support network operation, this standard use bus controller. Bus controller, it is a specific line replaceable unit which support data transferring between LRUs. It means that bus controller is like orbiter which guide data transmission in the channel. It means that bus controller specify which LRU should transfer the data to which another particular LRUs. Thus, bus controller do everything for performing package transferring. As usually on board of aircraft, we use reserved data channel. Thus, bus controller usually support a few buses for data transferring and in parallel. Thus, it can use one primary data bus and one or two or three standby data buses, and all the data are transferred parallel for LRUs. Also, based on multiplexing topology, each LRU can be like a switch for packages and can support their local subnetwork up to 30 LRUs. Thus, MIL-STD-1553 supports federated avionics architecture. What does it mean? It means that if we would like to transfer the data from one system to another, we can use this data bus to reach final destination cross subnetworks. Based on MIL-STD-1553, avionics architecture looks as following. We have a global data bus in which we have bus controller. We have a federation of avionics. Usually it is a group of avionics which required identical data. And inside of each federation we have local subnetwork of particular line replaceable unit. And then via this subnetwork, bus controller can guide packets from the main network to the extended subnetwork. And as you can see, here we can specify navigation group of equipment, we can see communication federation, we can vehicle control federation, probably electronic flight instrument system federation, and for example some military or weapons guidance network. What is different from ARINC 429? It is a level of signals, because a MIL-STD-1553B uses a specific signal coding, which called Manchester 2, and in this case it uses a sequence of two pulses to code logical 1 and a logical 0. Logical 1 is coded as a sequence of positive pulse and negative one. Logical 0 is coded as sequence of negative pulse and positive pulse. At the level of signal, we can talk that this logical 1 signal is opposite to the 0. At the signal level, we can specify this signal as C, and it means that this signal is a minus ST, which is opposite signal to the direct signal ST. The amplitude of both signals are specified at the range from 9 to 13 volts. The duration of one bit of information is 1 microsecond. What is the main advantage of Manchester 2 coding is reducing influence of noise. And how we can create Manchester 2 coding? In the simple way, we can do it by adding two signals with different frequency. We need to use signal of data at one time frame and another synchronized signal with reduced twice bit speed. And what we just need, we just need to put both of the signal to the logical operation of the inverted exclusive OR. And in this case, after it, we will get coding by Manchester 2. At physical level, we use two wires connection, and for one wire we use direct coded value. For another wire we use converter for rotation of our direct signal to the opposite one. Thus, by the second wire we transmit inverted signal to the signal in wire A. It gives a huge advantage. After transmission, in receiver side, we just need to extract one signal from another one. And if we make minus second signal from the first one, we will get double positive signal. Quite important that because both wires goes at the same place, A and B wire of physical level of MIL-STD-1553. It means that noise can act at the same way, and we have approximately the same noise level. And after the extraction of one signal from another, we make noise minus each from another, and it can reduce or even shut down noise in the channel. Thus, Manchester 2 coding helps not only support precise level of data transferred. It supports also reducing or deleting the noise influence. One more time, if we have signal ST and we have inverted signal ST at another wire, during the data transmission, noise will be 1. N from T, it is noise. After that, noise will be added to direct signal ST and added to negative signal ST. And in the receiver, we need to subtract one signal from another one. And in this case, ST plus NT minus ST, which means plus ST, and minus NT. Plus NT and minus NT can delete each other, and it means that we delete the noise from the channel. And at the end we will have double amplitude ST, and this is another advantage of Manchester to coding, because after that, first advantage, we get deleted noise, okay, most value, and the second one, we make amplitude of signal double time, and this is a great thing. If you talk about data word for transferring, it uses 3 different types of data words. Because we have bus controller, it means that bus controller should use specific word time to send commands for all the network. Thus, 20 bits data words are used in MIL-STD-1553. And the difference between these words is significant, and receivers can recognize the type of these data words by specific synchronization signal, which took first 3 bits. First type of data word, it is a command data word. The second one, just a data word. And the third one, it is a status data word. Command data word can be issued only by bus controller. Command data word, it is a command for all LRUs in the network to perform some actions. For example, setting up for transmitting or setting up for receiving data. First 4 bits from 4th to 8th contains the address of the LRU to which the digital word is sent. The address of ones is reserved and is used to identify the broadcast mode. Bit 9 indicates reception or transmission of data. It means that if we have 1, it means to transmit the data. If we have 0, it means that addressed box is required for receiving the data. Bit 10 from 10 for 14s are used to identify the information transmitted in the next bits. Zeros and ones is used to transmit a command, specific commands for these LRUs. In other cases, these bits indicate sub-address of LRUs in their local network of addressed LRU. It means that via these bits we can be switched from global to the local subnetwork of particular LRU if it is present. And finally, 20th bit is used as a parity control, as the same with ARINC 429. Data words are used for transferring data. And in this case, we do not need to specify what kind of data we need to transfer. Thus, data word includes 16 bits of data, and actually transmitter can put required data in this field and is ready for transfer it. Thus, here we do not have specific fields, only data. And of course, parity control. Also, we remember if we have more data for transferring, we need to use a sequence of data words. Thus, we can use long number of data, which requires a few or maybe much more than few, maybe 100 data words for transferring the whole sequence of data. And status word. Status words can be issued by LRU to specify a mode of LRU or its status. It means if this LRU is ready for transmitting, or if this LRU receive the whole sequence of data and this transmission was successful. It includes only two fields important for us. Thus, bits from 4 to 8 contain the address of LRU, which is carrying the word. And bits from 9 to 11 and from 15 to 19 are LRU bits according to specific coding table. Bits at the middle from 12 to 14 are reserved and not used. Data transferring according to this network is the following. It can be done in different modes, and if in case of data transferring from controller to LRU, controller just issue command word for a particular LRU and then generates a sequence of data words with the data. And after that, LRU which receives this data have to issue status word with indication that all transmission has been successfully. If you would like to transfer the data from LRU to controller, in this case, first of all, controller have to send control word about this transmission. Then LRU needs to specify its status to be ready for data transmission. And after that, this LRU will send a sequence of data words. And quite important that here we do not have status word, because bus controller does not require status word, because bus controller needs these words, and if bus controller receive the data words, it means it's know everything about this data transmission. Thus status words is not required. If we need to organize data transmission between LRUs, which is the most frequently used in network, first of all we need to send command word from bus controller to the network to both LRUs. Then LRU which will be transmitted, which will generate the data in the network, is required to generate status word, and it means that LRU is ready for transmitting, and then it will give digital data words with information. Amount of these data words can be different. And then at the end, LRU which receive the information have to specify status word that transmission was successful. In the case of broadcast mode, when we need to transfer the data from bus controller to all other LRUs in network, we do not need to use status word. Just bus controller issue command for transferring, and then just send digital data words. If we would like to use broadcast mode from LRU to all other LRUs in the network, we need to also receive command word from bus controller, then LRU which issue the data transmission needs to generate status word about readiness for data transmission and then begin data transferring. Probably that's all that we would like to talk about MIL-STD-1553. It is important because in historical development, MIL-STD-1553 it is a first network topology on board of aircraft because it operates with the packets, which means data words, and we can use a huge amount of the data. And actually, for this standard, it does not matter which sort of data we transfer. At the physical level, we do not have any specified fields for different types of data. Thus, it is important for network technology development on board of airplane. Next level of data modification in DDB is specification ARINC 629. And the main here that it is use time division access for the bus. However, first of all, this standard was published in 1989 and firstly used on board of Boeing 777. It supports speed of data transmission up to 2 megabits per second, which is twice time more than MIL-STD-1553B. This standard support network topology up to 120 LRUs. And of course, it uses Manchester to coding at the physical level of signal to get the best from MIL-1553. Yeah, I mean extracting noise influence or deleting noise and getting double power of signal at the receiver side. In this case, we use bus topology and all LRUs are connected parallel to two pair of wires, twisted pair of wires with active shield technology to the ground. Message structure of ARINC 629 includes three types of data. First of all, we need to specify digital message. All message can be divided into their strings. Thus, one digital message can be divided up to 31 digital string. Each digital string is divided into the digital words, and we can use up to 256 digital words in one string. Thus, any amount of data we can pack and transfer with the help of specification of ARINC 629. If we talk about data transmission, everything is quite simple. We do not have any bus controller. We have only small micro scheme in each LRU. Also, I would like to note that each LRU can be transmitter or receiver. Time excess gives a huge possibility. It means that each LRU in network, I mean up to 120 LRUs in the network, has particular time for transmitting the data. What does it mean? It means that any LRU has a specific time for using data channel for transmitting the data. And then inside of transmitting mode, we specify the sort of data. We specify, for example, destination, final destination address for this data. Thus, in ARINC 429, we have specific cycle of data transmission. In this cycle, each LRU in the network has possibility for transferring the data. And this cycle of data transmission is started from packets of particular LRU. Then when time slot for using bus of first LRU is over, then second LRU issue label with the name of its LRU to start getting access to the bus, and after that it will issue digital data message. After the ending time slot for second LRU, we will go to the third LRU, and the same idea. Then third LRU needs to issue number of module or name of module, and then it will issue the sequence of messages during the specified time frame for this third LRU. After the end of transmission, final LRU will initiate synchronized pulse. After this synchronization, all LRUs also will issue synchronized pulses, which gives possibility to synchronize cycles of each LRUs. Thus, it is distributed network technology in which without synchronization we cannot catch particular time frame to get access to the bus. Thus, at specific time we've got synchronization of all equipment and all micro schemes of ARINC 629, and then we count slots of time for each LRU after this synchronization. This is the main idea of transferring data in ARINC 629. And actually that's the most important thing that I would like to tell you about both of this channel. It is important that both of these channels, MIL-STD-1553 and ARINC 629, are quite different from ARINC 429. And all of these channels support more reliable network topology. The place of ARINC 429, mostly it is a direct data transmission. It is because we can use only one transmitter in the network. Thus, nowadays, when we have advanced network technologies, which is the next step of development, the place of ARINC 429 still present on board of aircraft, because there are multiple cases when we need to connect one sensor to multiple sources. As an example, some remotely installed sensors on board of aircraft. Thus, we can use one sensor, and we can connect this sensor with the help of ARINC 429 with different LRUs, and we can share the data, and we can perform faults during the transmission, and this is a great idea. Also, ARINC 429 is not complicated. It is simple. That's why for developers of avionics, it is actually very reliable things for simple data transmission. Thus, ARINC 429 still present, and it is still present for more than 40 years in avionics development, from beginning of digital electronics up to modern integrated architecture, because sensors will be present always, and always sensors will be located remotely. Even if we use integrated modular architecture, 429 still required on board of aircraft, because it is does not make any sense to use a global data bus for sharing some sensor data which is required only for small amount of LRUs. Thus, this standard and this specification helps to save performance of global data bus for more important data transfer. Therefore, we will see it in future in different development of on-board network topologies. A few words also we can add to using, for example, optical fiber at the physical level of data channel. Yes, it is present and it can support high-speed data transfer. However, it applied for global data bus very carefully, because it has some particularities of operation which we need to take into account during system maintenance and system development. Thus, wires connection and wires data buses is still present on board. Probably that's all for today. Thank you for watching. It was me, Ivan Ostroumov, with avionics equipment of civil airplanes. See you later. Bye.